Howdy. I want to talk a little bit about exponential functions here. We're going to start with a review of the algebra of exponential functions, and then we'll do a very small amount on the calculus of exponential functions. Exponential functions are near and dear to the heart of calculus folk for reasons that will become clear in this video. So, when we're talking about exponential functions, we're talking about functions that have a constant base, such as e, or 2, or 1/2, raised to the x power. Notice that this is the opposite of a monomial, which would have x raised to some constant power. So a monomial is not an exponential function because the variable is the base rather than the exponent. We also have a requirement on, so the general exponential function is going to be f of x equals b to the x. And we have a requirement on the base, and that is that the base has to be greater than 0. And the reason for that is that if I allowed, for example, the base to be -1, if I had g of x equals -1 to the x, then I would end up with all sorts of strange things. For example, g of 0.5 would be -1 to the 0.5, which is the same as the square root of -1, which is not a real number. To avoid these unfortunate types of things, we exclude negative numbers from our bases. Okay, well, if b to the x is our exponential function, then what does the graph of b to the x look like? Generally speaking, you're going to have two shapes to your exponential graphs. If b is a number greater than 1, then my graph is going to be an increasing graph with positive slopes of tangent lines. And the reason for that is simply that if my value b is greater than 1, then as I multiply it by itself x times, which is the integer sense of exponents, then I'm going to get an ever-increasingly larger number here. So that's the intuitive argument. If, on the other hand, b is less than 1, then as I multiply b by itself x times, as x gets larger, then b to the x will get smaller and smaller. Notice that in both cases, the graph passes through the point 0, 1. And in both cases, the graph has a horizontal asymptote, y equals 0. Here we would say that the limit as x goes to negative infinity of b to the x is equal to 0 for b greater than 1. And we would say that the limit as x goes to positive infinity of b to the x is equal to 0 for b less than 1. There's a b that I missed. What happens if b is equal to 1? I'd like for you to take a minute, pause the video, and sketch a graph of y equals b to the x when b is 1. Welcome back. If you sketched it correctly, you should get a nice constant function that neither increases nor decreases. Well, if b to the x is an exponential function, then what is its inverse? The inverse of b to the x is called the logarithm base b of x. And we will have a lot more to say about logarithms after Thanksgiving. But for now, we want to simply observe the inverse relationship. If I apply log b to the function b to the x, they cancel and give me x back. If I raise b to the log base b of x, the two functions cancel and give me x back. Now, this is useful for solving exponential equations. For example, if I have 4 times 2 to the x is equal to 5, and I want to solve this equation for x, then I'm going to proceed by isolating the exponential. By dividing both sides by 4. And then canceling the exponential by taking the inverse of both sides, that is log base 2. So if I now take the log base 2 of both sides, then these cancel, giving me x, which is equal to log base 2 of 5/4. That's as simple as we need to have it for now. So we put a box around it and smile. Now, you may wonder, what are the properties of the exponential function? And I want to give you 3 plus 1. The 3 are going to be the multiplication, division, and power properties. And they're very familiar to you. You've been doing them since Algebra 1. If I multiply b to the x times b to the y, then the exponents add. If I divide b to the x by b to the y, the exponents subtract. And if I raise b to the x to the y power, then the exponents multiply. These are the big 3 properties of exponents, and we use them all the time. I want to add one additional, which is a change of base. And the change of base property allows us to convert from one base of exponential to another. So if I have a to the x and I want to represent it as b to some power, then a to the x is equal to b to the x times log base b of a. Now, why is this? Well, actually, it's fairly simple to see if we leverage our power property from right here. Because I can write b to the x log base b of a as b to the log base b of a to the x power. And this is a to the x. In particular, we're going to find this very useful when we come to the natural base of exponentials, which is e. Tomorrow, I'll give you a short history of where e comes from. But e is an example of a transcendental number. It is irrational, meaning that it does not repeat. These 4 digits that you see here, 1828, 1828, are followed by 3 something something. It does not repeat, so it is irrational. And not only is it irrational, but it is also not the solution to any polynomial equation. So it is not an algebraic number either. It is a transcendental number. And so if we use this change of base property that we have above, then we can say that all exponentials, b to the x, are basically e to some power, specifically e to the x natural log of b. Notice the natural log here. means the same as log base e. And the reason we call it the natural log and use the symbol ln here is that e is the natural base of exponentials, as we shall see in just a moment. Okay, well, so much for the algebra of exponential functions. I want to do two very quick calculus things. The first is that I want to make a claim that I'm going to ask you to use your calculator to make plausible. So pause the video for a second, get your graphing calculator. And what I would like for you to do is to evaluate this limit on your calculator. Now, in case you're a little bit rusty on that, the way in which you evaluate the limit is to let y1 equal the particular function. Notice that the e to the x function is built into your calculator. And then you're going to investigate x values that are very close to but not equal to 0. Take a moment to do that, get a value for the limit. Pause the video while you do that, and come back when you're done. Well, if you've done everything correctly, then you should have found that this limit is in fact equal to 1. I am going to just take this as a fact. We actually prove it in Calc 2. But I think that it's plausible enough from the evidence of your calculator. So this is our third special limit. You recall the other two special limits were the limit as x goes to 0 of sine x over x equals 1, and the limit as x goes to 0 of 1 minus cosine x over x equals 0. So we have our triad of three special limits. Now, the reason this limit is particularly special is that it allows us to evaluate the derivative of e to the x. Let's think about this for a second. E to the x exponential function, can I use the power rule on it? No, I cannot, because the power rule requires that x be the base right here, and that I have a constant exponent that is exactly the opposite of my situation right here. I have a variable exponent and a constant base, and I have no reason to suppose that the rates of change for these two types of functions would follow the same rule. And in fact, they don't. Instead, I'm going to need to go back to the limit definition. This should be the limit as h goes to 0 of f of x plus h minus f of x all over h. Notice that f of x plus h here is e to the x plus h. Now I look at this e to the x plus h, and I say, hey, I can do something with that with the product rule for exponentials. E to the x plus h is the same as e to the x times e to the h. And then I look further and I say, look at that, I've got a common factor of e to the x here that can be factored out. And in fact, it is a constant with respect to h because it does not have any h's in it. So out that comes. And the quantity that is left, lo and behold, is exactly the special limit that you found on your calculator just a moment ago. And that value is 1. So that I end up with this result. The derivative of e to the x is itself. Wow. That is actually pretty special. The reason that this happens to work out is because of our special limit. And the reason that our special limit works out, well, that you'll have to wait until you take Calc 2 for. Now, the question is, are there other such functions whose derivative is themselves? in third quarter, we're going to investigate that question a little bit more thoroughly. The answer turns out to be no. That within a multiplicative constant, in other words, if I have a constant times e to the x, then, of course, using the constant multiple rule, its derivative will be a constant times e to the x. But leaving aside the multiplicative constant k, e to the x is the only function whose derivative is itself. Well, the last thing that I want to do is to consider how this works out with chain. So, for example, what if I have the derivative of e to the 3x? Well, using our chain rule, that should be the derivative of e evaluated at 3x times the derivative of the inside, which is going to be e3 e to the 3x. Same story if I do something more complicated. The derivative of e to, let's say, the square root of x is itself times the derivative of the inside, which is 1 over 2 root x. No, not 2 root 2. 1 over 2 root x e to the root x. And in particular, we can leverage this to find the general exponential derivative. The derivative of b to the x can be found using our change of base. If I change the base to e, like so, then I now have itself times the derivative of the inside. Keep in mind that the natural log of b is a constant because the base of an exponential is a constant function, and so the natural log of a constant is just a constant. So what we really have here is natural log of b times the derivative of x, which is just 1. But wait, there's more. Because this factor right here is the original exponential, which is equal to b to the x. And so we have that the derivative of any exponential b to the x is equal to itself times the natural log of the base. Does that work out for e to the x also? We know already that the answer here should be e to the x. Using our form that we have here, we get e to the x times the natural log of e, and the natural log of e is 1. So all is